Welcome to the channel RIK Learner for KCET NEET. A block of mass m is suspended by means of an ideal spring of a force constant k from ceiling of a car which is moving along a circular path of radius r with acceleration a. The time period of oscillation of the block when it is displaced along the spring will be. See the drawing in which we are seeing a spring attached with a mass m. If the car is in rest, otherwise it is moving in a uniform motion, the position of the spring would be along the this line. What I can say, it is in the direction of acceleration due to gravity, that is vertical line. Now when the car is about to turn in a circular path, so when the car is turning to the right like this, and this mass that is attached with the spring will move in this direction. Okay, so it will move in this particular direction. Okay, so in this situation, how we have to find out the exact answer for the time period of oscillation? Okay, so now what I say, in the static position, otherwise when the spring is in rest, this is called equilibrium position. Okay, so in this situation what happens, the upward force in the spring, that is the restoring force, which is given by minus kx, which is exactly equal to the weight of this block mg. Okay, so these two are equal, so w is equal to f, otherwise f is equal to w. So there is no oscillation. Okay, no oscillation. If the situation is different, that means if the spring is extended a little, right, from its initial position, okay, we are extending it somewhat. At this situation what happens, the restoring force in the spring, it's acting upward, that we cannot see, no doubt. So that force is, again we write it minus kx. Okay, so where x is the extension what we are seeing here, and the weight is here, which is mg. As soon as I release this block from my hand, this block will move up. Okay, so it will move up in upward direction, right? So with some net force, which is equals m into a net, so it's the net acceleration. This happens when, okay, so this is true when the upward force, that is restoring force, is more than the weight. As soon as we release it, at that moment it will rise up. Okay, so the block will rise up. So this is what happens in this kind of situation. What we can do, the net force on the block is ma net, which is equal to the magnitude of the spring force, which is kx. Okay, so I'm simply taking the magnitude, and a net is equal to what? It is k divided by m into x. But as we know, this spring, when it is released with this mass, the mass simply goes up and come down, right? It will move up and come down. So this will make a simple harmonic motion. In any simple harmonic motion, the net acceleration is always proportional to the negative of the displacement. Otherwise, we write a net is equal to minus omega square x, where omega is 2 pi by t, right? So in this situation, what we can do, a net is this thing. The magnitude of a net is simply what we can write. It is omega square x. So if I use here omega square x is equal to k divided by m into x. So definitely the term x get cancelled and omega square becomes simply k divided by m. Otherwise I can write omega is equal to under root k divided by m, or simply it is 2 pi divided by t, which is equal to root of k divided by m, or t is equal to 2 pi root m divided by k, right? So this is the period of oscillation what we got in this situation, where there is no acceleration or the body is moving uniformly. Okay, so then only we will get this particular equation. Okay, so this is in rest or in uniform motion. So in this question, it is said the spring is attached to the roof of the car and the car is moving in a circular path of radius r with acceleration a. Okay, so acceleration is a. That means the net acceleration is a. In this situation, what we can think is, here is the roof of the spring, and this is the vertical. The spring could be written here as is shown, and here is the attached mass, right? Here is the attached mass, and be careful, the acceleration due to gravity is acting downward, and the pseudo acceleration is in this direction. Then the net force is acting in this particular direction. This is the direction of the net force, and this net force, which is net acceleration, is again equal to minus omega square x, as we did in the earlier situation here, what we already did here. The same thing is true one more time in this situation, right? So here will be the spring force, right? So this one, again what I can write. So in this situation, as soon as I observe that the spring is extended and released, so again the spring will oscillate. So again I have to follow the same steps above, the same steps, right? Steps above. So one more time I get the same equation, that is t is equals to pi root m divided by k. Because when I was deriving this equation, so the term acceleration, otherwise net acceleration, is not appearing anywhere. That means whatever the acceleration of the car that we expect, that will not appear in the result. So that means the period of oscillation is independent of the acceleration of the vehicle. That means definitely option C, what we are seeing here, is correct.